All right, question 21 on the math subject GRE practice test. This is kind of a fun problem. This deals with modular arithmetic, which is just a cool section. So I think what I'm going to do here is similar to what I did, I think it was the last video, where I solve the problem kind of quickly and then I go back afterwards and kind of fill in some gaps. So what we're told is that x and y are integers, and 3x plus 2y is congruent to 5 mod 13, and x plus 7y is congruent to 1 mod 13. What we're asked is what 5x plus 3y is congruent to. Again, mod 13. So first off, I'm sure there's some clever way to figure out what 5x plus 3y is congruent to without ever figuring out what x and y themselves are congruent to. But sometimes on tests like this, it's easier to do it the more kind of standard way than trying to be too clever. So maybe I'll leave the cleverness for one of you in the comment section, and instead I'll just solve for x and y and get my answer that way. So if I stare at these two equations, or I guess congruences, what I want to do is solve one of them for one of the variables. Doesn't matter which equation, doesn't matter which variable. The one that jumps out to me as easiest to solve for is over here, and that's because the coefficient on x is just equal to 1. So solving this for x is as easy as just subtracting 7y from both sides. I get that x is congruent, mod 13, but since everything's going to be mod 13 in this problem, I'll just omit that to 1 minus 7y. I can now plug in 1 minus 7y for x over here and get 3 times 1 minus 7y plus 2y is congruent, mod 13 to 5. If I distribute and collect like terms, I got 3 minus 21y plus 2y is congruent to 5. So negative 19y is congruent to 2. Subtracting 3 from both sides of the equation and combining these like terms. At this point, you might be thinking that solving this system of congruencies is identical to how you would solve a system of linear equations. And I guess so far it is, but here's where things get a little bit different. You can't just divide both sides by negative 19. Division isn't a thing in modular arithmetic. More on that later. I think instead what you'd want to do is add 26y to both sides of this congruence, 26 being a multiple of 13. So that tells me that 7y is congruent to 2. Note, you don't have to write the 26y over here because 26y is congruent to 0 mod 13. You're like, cool, you got a slightly smaller number and it's not negative, but you still haven't solved for y. And you told me you can't divide by 7, so what are you going to do? Well, the trick here is to multiply both sides of the equation by 2. That gives you 14y is congruent to 4. But 14y is congruent to just 1y, so I get 1y is congruent to 4. Once I know that y is congruent to 4, I can plug that into either equation and solve for x. Again, I'm going to choose this equation because the coefficient on x being 1 is going to make things work out really nicely. So since x plus 7y is congruent to 1, x plus 28 is congruent to 1. If I subtract 28 from both sides of the equation, I get x is congruent to negative 27. And if I add, let's see, 39, I guess, because 3 is the least multiple of 13, that will make this positive. To both sides of the equation, I get that x is congruent to 12. And I guess I shouldn't say both sides of the equation, I should say both sides of the congruence, but you know what I'm talking about. Now that I know x and y, I'm ready to finish the problem. The problem asks for 5x plus 3y, but x is just equal to 12, or congruent to 12, I guess, and y is congruent to 4. So 5x plus 3y is congruent to what, 72? Subtract some 13s and we're done. Let's see, 13 times 2 is 26, and 26 times 2 is 52. So this is congruent to 20. Subtract one more 13, and we get that this is congruent to 7. Yeah, we probably should have subtracted 5 13s at this step, but 4 13s was easier for me to do in my head. Anyway, 7's our answer. 7 is C. We're done with the problem. A couple things that I want to comment on. The first one is at this step, I got that 7y is congruent to 2. If you're paying really close attention, you might have noticed a 7y over here. I really didn't have to solve for y. I could have grabbed this equation right here at this point and written x, and then instead of 7y, could have written a 2 is congruent to 1 mod 13. Subtract 2 from both sides, you get x is congruent to negative 1. In other words, x is congruent to 12. All right, I'd argue that this path is a lot more direct than continuing here and then going up this way. The last thing I want to talk about before I finish this video is just modular arithmetic in general. I think most people taking this test are really comfortable solving systems of linear equations in 2 variables. What I'm saying is if this was an equal sign and this mod 13 weren't here, and similarly this were an equal sign and the mod 13 weren't here, you'd have no problem with this problem. Most people who struggle with the problem do so because they're not 100% sure how to deal with this kind of triple equal sign. Well, in short, modular arithmetic works a lot like kind of normal arithmetic. And I think rather than kind of memorize the rules, like what exactly can you do and what you can't do, if you just sort of understand what's going on, the rules make perfect sense. So when you see this mod 13 right here, we're essentially just talking about the remainder when you divide by 13. So additional multiples of 13 don't even come into play. It's just the remainder that we care about. So since 13 is congruent to 0 mod 13, we can add or subtract any multiples of 13 to either side of the equation, or I guess either side of the congruence. To go from this line to this line, I added 26y, but it kind of looks like I only added to the left side. Really, you could think about it like I added 26y to both sides, but the 26y that ended up over here is congruent to 0, so I don't even need to write it. And that's true whether you're talking about multiple 13s of your variable or multiple 13s of a constant like negative 27. I added 39 to both sides here. That 39 changed the negative 27 into a positive 12, and the 39 on this side is just congruent to 0. So you can think about that as 0 plus x. That's the big thing you can do that you can't do when you're solving systems of linear equations. The big thing you cannot do is you can't divide, right? In this step right here, I can't divide both sides by 7 and say y is equal to 2/7. And the reason you can't divide is because that congruent 7y is congruent to 2 mod 13. What that really means is that 7y equals 2 plus some number of 13s. I don't know how many 13s, right? I'm only considering the remainder here, this 2. But really what this notation means is this for some integer n. So think about what would happen if you try to divide both sides by 7. This would turn into a y, this would turn into a 2/7, but this would turn into 13/7 n. We no longer have the remainder upon dividing by 13, so for that reason you can't divide both sides by 7. So what can you do? Well, anytime you're thinking, man, I really wish I could divide both sides by something, instead just multiply. A cool thing that happens with modular arithmetic when your mod is a prime number, which it will always be in these problems, is that for any number from 1 to 1 less than your mod, in other words, the numbers for which all integers are congruent to, other than those integers that are congruent to 0, there will always be another number in this range that you can multiply the first number by and get something congruent to 1 as your answer. You don't need to list those all out, but you can. It's pretty straightforward. 1 times 1 would give me 1. 2 times 7 would give me 1, because 7 times 2 is 14, and 14 minus 13 gives me 1. Because 2 times 7 gives me 1, 7 times 2 must give me 1. Let's see, for 3 times 5 gives me 15, and 15 is congruent to 2 mod 13, which I've already figured out has a multiplicative inverse of 7. So what I'm saying is if I started with the 3, I could multiply it by 5 and then by 7, and I'd be guaranteed to get 1 as my answer. In case you don't believe me, 3 times 5 is 15, and 15 times 7 is 105. And 105 is just 13 times 8 plus 1 more. So 3 times 5 times 7 is congruent to 1 mod 13. What I'm saying is a multiplicative inverse of 3 would be whatever 5 times 7 is, 35. And you're like, wait a minute, I thought you said there was a number from 1 to 12. Well, yeah, but I can reduce 35 mod 13 by subtracting 13s. If I subtract 2 of them, I get 3 times 9. What I'm saying is the multiplicative inverse of 3 should be equal to 9, and the multiplicative inverse of 9 should be equal to 3. We can check to make sure that works. 3 times 9 is 27, and 27 minus 26, sure enough, gives me 1. All right, you can kind of keep playing this game to sort of fill out this table here. It's kind of fun to do, because there's so many ways you can get to the same answer. Like for 5, for example, I just figured out that 3 times 5 times 7 equals 1, or is congruent to 1. So 5 times 3 times 7 must also be congruent to 1. In other words, 21 is a multiplicative inverse of 5. And if I reduce 21 mod 13, I get 8. So 5 and 8 must be multiplicative inverses. Oh, right, 8 times 5 is 40, and 40 minus 39, 3 of these 13s, give me 1. 5 and 8 are inverses, 8 and 5 must be inverses. The point that I'm making, I think I'm having more fun with this than I should, is that all of these numbers have multiplicative inverses. Kind of interestingly, in the case of 12, it's just 12. Whoa, how'd you do that so fast? Well, 12 is congruent to negative 1 mod 13, and negative 1 times negative 1 is equal to positive 1. So 12 and 12 must be multiplicative inverses. Nothing special about 13. That works for any mod. 1 less than that value, because it kind of acts like negative 1, is its own multiplicative inverse. Right? This stuff is kind of fun. Anyways, the point that I'm trying to make here is, instead of dividing, what you do is you just multiply by the multiplicative inverse. So up in this step right here, when I had 7y was congruent to 2, instead of dividing by 7, what I do is I multiply both sides by 2. 7y times 2 is congruent to y. Anyways, there's a little bit about modular arithmetic, a topic that I think is really fun.